Hello, welcome to the second lecture of the NPTEL course Fundamentals of Composite and Cellular Materials. In this lecture, we will cover the topics Material Selection Basic for Design with Hybrid Materials. In the previous lecture, we discussed the following topics. We first discussed the use and the definition of the hybrid materials. There we saw that if we fill up the material property charts with only the classical bulk materials like metals, ceramics, polymers, glasses, etc., then there are many void spaces which cannot be filled up by those bulk materials. As a result of this, we develop hybrid materials. The hybrid materials can be again be like composites or cellular solids, and these actually allow us achieving properties and domains which are not possible with conventional bulk materials. We also discussed about the fundamentals of composite and cellular materials. Now, in today's lecture, we will cover the following topics. We had a brief discussion of the cellular materials in the last lecture, and today we will complete the classification and basic benefits of cellular materials. These topics will again be discussed in much detail in the next lectures. In the second part of today's lecture, we will cover the aspects of material selection for design purposes. This is important because you will see that with hybrid materials, we get into a totally new domain of materials design, and for that it is important to understand how materials are selected for design purposes. And the last and final step of today's lecture of this lecture will be steps involved in materials selection process. The basic keywords for today's lecture are here: honeycombs, foam, lightweight, edges of materials, material selection basics, and material selection steps. Now, in the last lecture already we saw that the cellular materials can be classified into three main groups. Ideally, cellular materials are defined as an interconnecting network of struts and plates which actually make the cell walls and the cell faces. And the cellular solids typically also contain a significant amount of porosity or void, which is typically more than 70%. Now, honeycombs are typically defined, as you can see on the extreme right hand side. This is a typical photograph of an honeycomb. A honeycomb is nothing but an array of polygons which fill space like the hexagonal cells of a bee. That means the beehive is a typical example of a honeycomb structure, and you will see afterward that the honeycombs are excellent cellular materials and they provide excellent properties if designed properly. In contrast, the foams, in foams like being shown on the extreme left hand image and the middle image, in the foams the cells are polyhedral which pack in 3 dimensions to fill the space. Foams can again be classified as open cell foam and closed cell foam. If the solid of which the foam is made is contained only in the cell edges, then it is an open cell foam. As you can see, the middle picture of this photograph or this slide shows an open cell foam. Whereas, if both the cell edges and the cell faces contain solid material, then we obtain a closed cell foam. Typically, I mean most of the cells that you see on the left hand side image is they are closed cell foams. At the same time, you can see that in a real foam, because of fabrication difficulties, a real closed cell foam is almost never completely fully closed cell, because there might be some fabrication related defects, there might be thinning of the cell faces, and for that typically in a closed cell foam we have partly closed cell and partly open cell foams. The mechanical properties of the closed cell foams and open cell foams and how the structure actually affect those properties will be discussed in the future lectures in detail. Now, the next question is, why are cellular materials important? In the last lecture, we already discussed that cellular materials are very known to us from nature because many of the materials around us, they are actually cellular solids. Like we gave the examples of wood, then mushroom, our bone in the body, then the skull, these are all actually examples of cellular materials. Now, cellular materials actually they can actually provide extremely good properties if the material can be designed in a proper manner, and some of these properties can actually be not attained by also bulk materials. Now, typical properties of cellular materials are mentioned over here. The first and foremost important property is the lightweight. So, cellular materials, because they contain a large amount of void or pore space, as I just mentioned, that typically the cellular materials contain more than 70% air, and as a result of that the cellular solids are very low density. Typically there are cellular solids which have been fabricated which possess even density less than 10% of the bulk cell wall material. Cellular materials also possess a very high specific stiffness. So, specific stiffness means, as I discussed yesterday, this is nothing but the parameter E over rho, where E is the Young's modulus and rho is the density of the material. Now, definitely cellular materials will have, because of large amount of air, they definitely have lower modulus than the bulk metal or the bulk solid of which the cellular solid is made of. But because of the fact that they also contain very low density, this E by rho parameter of cellular solids are reasonably high, and in many cases there are also other properties like e to the power half over rho or e to the power 1 by 3 over rho. These properties of cellular solids, which are important for many specific stiffness applications, they can actually they can actually improve upon the properties of the bulk metal. Cellular solids, some of the solids like cellular metals, if designed properly, they can also provide excellent energy absorption capability. It will be discussed in detail in the future, but again just for here, so typically the stress strain plot, a compressive stress strain plot of a cellular metal or a metal foam looks something like that. So, you have an initial elastic region which is theoretically called linear elastic, but you will see afterward that it is not really linear elastic, but anyway for now we consider it to be linear. And then this is a typical feature of the cellular solids that after this region there is one region where the stress remains almost constant over a large amount of strain, and then if you deform further, then this region appears, which is called the densification. Now, if you see that the area under the stress strain curve is basically nothing but, if you see, this is the area under this curve, and because the cellular solids have a very large amount of plateau region, they typically contain, they can typically absorb a large amount of energy, which is nothing but the area under the stress strain plot. Also, cellular materials possess low thermal conductivity. That means they are extremely good as thermal insulating materials. Why so? Because as you can imagine that in a material with significant amount of air which has a very low conductivity, the conductivity of the bulk material or the bulk cellular solid will definitely be lower. That means the presence of large amount of air also renders the cellular material good insulating behavior. Also, cellular materials are very good for sound absorption. You will see afterward that these open cell foams, I mean we have to here differentiate between the properties, like the closed cell foams like the left hand side, they are typically used for the mechanical properties or structural applications, whereas the open cell foams, they are very commonly used for your functional applications. Now, the open cell foams, as you can see in the middle image, they are extremely good for sound absorption, because as sound energy is incident on the cellular solid on the open cell foam, as the sound energy enters the material, because of multiple reflection and refraction, the sound energy loses its energy, and that is why the cellular solid works very good as a sound absorbing material. And also some cellular ceramics, like ceramics, you know, they are very poor for thermal shock resistance, because ceramics typically have low fracture toughness, and if and also they have typically a high Young's modulus. That means if a ceramic material is kind of shocked from a high temperature to low temperature, they are very prone to failure or cracking. But a cellular ceramic with a large amount of air in the material, they are very good as thermal shock resistance, because the large amount of void present in the material, they actually do not let the crack propagate in a catastrophic manner, and the material can sustain for a longer period over a large temperature range. So, that means this slide basically shows that the design aspect of cellular materials is extremely important, and if we can design properly, we can obtain a material which is excellent in many functional applications and structural applications, and we can also combine different properties in the same material, which is actually pretty difficult to obtain in the normal bulk materials. Now, with this background, so now that means if we now again go back to our previous lecture, where we saw that we had the bulk materials and now we also have the hybrid materials. Like we had already the bulk materials like metals, ceramics, polymers, elastomers, glass, etc. And now we also add upon them the cellular materials and the composite materials. This actually makes the whole set of the material universe extremely vast. So, this slide basically shows that how the relative importance of different materials have evolved from prehistoric time like before 10,000 BC to the current time, and the width or the height of the individual domains actually show that the importance of the different materials to the mankind in various ages. So, here you can see that the prehistoric man, the earliest cases, we had the stone ages, because at that time stone was the only material which was known to mankind. But then as human become more and more advanced, then we developed more and more materials, but again the materials always played a very important role, and that is why the various ages of civilization are named in the terms of like bronze age, then iron age and so on. Now, one very important aspect that I would like to draw your attention is the time period between 1940s and 1960s. So, basically in this time period is very important for current civilization and current industrialized world, because that was the period where many of the developments technologically took place because of the aftermath of the Second World War. What we see around 1940, we can see that although we started initially with the non-metals like stones, wood and so on, but around 1940 and 1960, at that time actually metals were the majority of the material used for all the applications. But then as technology more and more improved, we realized that there are other options, and then actually as we see today, the importance of metals have not diminished, because even if we see around us, we see that most of the components like the structures, our vehicles, all the things or most of the things that we see around us, they are actually made up of metals and typically steels. But despite the fact we see that as we have entered into the 21st century, there are other materials like composites, they are becoming more and more important. And these composites, which are the hybrid materials, they will be even more important in the future years. And that is why our knowledge about the composites, or in totality about the hybrid materials covering the composites and the cellular solids, are extremely important. So, now for a material selection, it is not only important that we identify the optimum material, it is also important that how a component is fabricated from a material. That means there are many other, this is not only the material selection by a metallurgist or a material scientist, there have to be also other factors considered, like how the materials will be shaped, joined or machined. Like you know that a ceramic might have excellent properties, but it is very difficult to shape or join the ceramics. Again, there are other aspects like cost is a very important factor. Like if you consider only the properties of the material, maybe carbon fiber reinforced carbon or those materials are extremely good and they will outperform many of the metals. But do we really fabricate many of our day-to-day items or equipment with carbon fiber reinforced composite? We simply can't afford the cost of the material. Environment also plays a very important role, because how does the raw materials are fabricated, and also it does not end with that. It is also, I mean, in today's world with significant amount of greenhouse emission and all those aspects, we have to also consider that once a material has been completely used, how the material will be kind of recycled, if it is at all possible to recycle. That means, if a material is not recyclable, that will actually add on to the material load to the whole environment. So, it is not again kind of appreciated. So, keeping all those things in mind, it is extremely important that we develop a systematic procedure to develop the materials selection knowledge, and this will be basically discussed in the next couple of slides. So, now the question is that what is the procedure or what is the systematic procedure to design a material or design a component from any material. Now, the first point of any design process is the identification of the market need or the design requirements. That means, first point comes from the requirement. That means, the necessity is the mother of all invention. That means, we have to first identify for which application a new material has to be developed. It might be, for example, high temperature aerospace applications, or for example, it can be a simple spring which is also lightweight. It can also be something like a wheel for the automobile, something like that. So, in any case, for any material design, the first and foremost thing is the market need identification. Once the market need identification has been established, the next process is the concept development. In the concept development, here all the available concepts should be considered, and then based upon that, at that point the best or the most suitable concepts are kind of transferred to the embodiment stage. That means, in the embodiment stage, maybe a model will be developed, maybe a CAD design will be developed and will be subjected to some kind of load by finite element modeling. So, all those kind of things will be done in the embodiment stage. Then once this stage has been performed satisfactorily, next come the detail stage. That means, in the detail stage, what will be done? In the detail stage, the complete fabrication of the component will be systematically developed. There will be plans and programs of, there will be kind of parameters how to fabricate the component, and that will actually lead to a complete product specification. But life does not end over there. In many cases, the product which has been developed after this first round of this concept, embodiment and detail stage is not good enough, because it is not fulfilling the customer requirement. Then that means, it will be completely continuously iterated. That means, the whole process will be repeated, and even if you fulfill the customer requirement, then there may be further improvement, because technology never stops. If material development is stopped by one company, there may be other companies who will come and perform or fabricate a better material, which will kind of put the previous company out of the market. So, that means, this materials development and all these processes kind of go on continuously and iteratively. Now, in this complete process actually the materials selection plays a very important role. So, that means, the earlier stage or the earlier slide what I discussed was about the steps involved in the component development. Now, we come to the stage of only one aspect of the component development, that is the materials selection aspect. That means, how to identify the ideal or the optimum material for any application. Again, this is not a very trivial job. Why? Simply because we have a huge array of materials which are available to us. If you see the current material palette, there will be more than 150,000 different materials which are available to a materials engineer or a material scientist, from which he or she can develop a new component or a new material. That means, at the beginning, the first stage is the translate design requirements. That means, once you have identified the design requirements in the previous section or the previous product development stage, then these will be actually transferred to the materials selection stage, and at this stage all the materials should be considered. That means, you do not want to lose upon any particular material at this initial stage, because if you simply kind of reject one material, that material might be the best material afterward. So, you do not want to reject any material at this point. After the first step, this where all materials are kind of considered, the second step is the first screening using constraints. So, this we will be actually seeing in the next slides. The third step is rank using objectives. The fourth step is getting supporting information, and once you reach this fourth stage, you will see that only few materials are remaining which are actually fulfilling your all the requirement. And after that, after you identify those few materials, you make the final selection based on local constraints. There may be cost constraints, there may be technological constraints, so all those things will be there, and this way you will end up with only one or two final selection from which you will identify the best material for your application. Now, these individual steps I will just kind of briefly discuss in individual slides. Sort of, as I just mentioned, the first stage is the translating of the design requirements. So, it all starts with a function statement definition. So, what is the function statement definition? The function statement definition actually tells you what task is the component expected to perform. So, as I already mentioned, it might be, for example, a component of a high temperature aerospace engine, or it might be a component for the brake of an automobile, it might be one component for a ship floating on the water, and so on. The next point is the constraints. So, constraints are basically either non-negotiable conditions or the negotiable conditions. That means, what are the non-negotiable conditions? Typically, for example, if you want to design a material for high temperature application, you will always have to keep in mind that the material must have very high melting point. That means, if your constraint is that you want to fabricate a material for high temperature aerospace applications or for aero engine applications where you reach more than 1000 or 1500 degrees Celsius, no polymer or almost no polymer should be used. There can also be like that you want to fabricate the chassis of your automobile. Now, this automobile body, the car body should be kind of tough and deformable because you have to give shapes. So, automatically most of the ceramics will be eliminated, because none of the ceramics, even if you do the strengthening or toughening by adding a second phase, none of the ceramics will be good enough to actually survive the loads or the stresses involved in the fabrication of the chassis. There can also be some negotiable but desirable criteria. What are those? For example, for aerospace applications, it is always a plus if the material possesses a low density. That means, in spite of the fact that there are two materials which are giving you equivalent high temperature properties, the material with the lower density would be more suitable for an aerospace application. That means, these are the constraints or negotiable constraint. After that, the next step is the objective. Objective actually tells you what is to be maximized or minimized. That means, this maximization or minimization, it can be one single property or it can be a combination of different properties. One example or two examples are being shown over here, like performance limited by a single property. As I just mentioned, suppose you are fabricating a material for a ship hull fabrication or maybe a kind of a lightweight application where weight is a very important factor, like in many aerospace applications. And there actually you should go for a material with a low density. That means, if none other constraints are kind of considered, for a lightweight application, density is a very important factor, but this is only one factor. And this might be very simple, and normally in industrial or kind of in real material selection, there is never a single property which will actually determine your material selection. So, in most often you will have performance limited by a combination of properties. What are the combinations of properties? That means, for thermal shock application, for example, what you need a material with a high thermal conductivity and a low expansion coefficient and also a low Young's modulus, because this way you generate less amount of thermal stress in your material. That means, the thermal conductivity K over alpha lambda, if conductivity is K and your alpha is your CTE and your Young's modulus is your E, then actually this parameter, if you maximize this parameter, that will actually provide you with a good thermal shock resistance. Another important application is for the spring fabrication. Now, this is a very interesting application. So, basically for springs, what you want a material with a high elastic energy storage capacity or rather a high resilience. Now, typically resilience you can find out from a stress strain plot. So, if you draw a stress strain plot of materials, you initially get a linear elastic region, and then if the material is plastic like typically metals, you end up in the plastic zone, right. And now this area, that means this area under the linear elastic region, this area is called the modulus of resilience, and the higher the modulus of resilience, the better the material for the spring application. Now, what is the typical formula for the area of this region? You can see this is half of sigma into epsilon, and because it is now following the Hooke's law, so you can simply write that because your epsilon will be becoming a sigma over E, so basically it becomes your sigma square by 2E. So that means materials having a very high yield strength and a low Young's modulus are ideal or good for your spring application. We can further optimize, like we want to have a spring which is apart from having a good spring constant, which is also having a low density. So, what we can do? We can further normalize this by rho, that means sigma square over 2 E rho will give you the material for lightweight spring applications. We can do further optimization, like we can also do like which materials will give you a spring at the lowest possible cost. So, we can also add one cost factor below, and those materials which are giving the best properties of this sigma square by 2 E rho C, these are the, this is now becoming your objective parameter, and you can then rank the parameters based upon this whole parameter, whole combination. So, then you have done the third stage, which is the ranking using objectives, and you see already that already after this ranking after objectives, the next stage is the getting supporting information, because as I mentioned, it is never, a material selection is never a single property game. You have to always consider many properties, like you will see afterward that in this slide, for example, you see over here the top table actually shows you if you only consider the spring as a material, that means you do not consider the density as a parameter, you want to maximize the quantity sigma f square over E, and you can see that there are materials like rubber or CFRP in spring steel, they are pretty good. But now if you now bring into factor like your density of the material, because steel has a very high density, suddenly for the parameter sigma square by rho E, the spring steel has very low values and the rubber has a very high value, also followed by materials like CFRP. But as you know, CFRP is a very high cost material, that means if you now put this CFRP price in this expression for C, probably you will lose the utility of CFRP for those particular spring applications. So, that means, and again for rubber, you might think that rubber is an ideal spring, but you have to keep in mind that rubber has a very high loss coefficient, and also rubber is pretty bad for high temperature applications. So, all those parameters you have to keep in mind, and when you design your new hybrid materials, your hybrid material design will actually have to follow these materials selection conditions. Now, this is the final step. So, final decision based upon local conditions, that means you have identified one material, but this is not the end of the job, because this material has to be fabricated. There has to be a workshop which is able to fabricate those materials, and it can be possible that you do not have sufficient raw materials for the particular material you want to have at that particular location, or for example, the workshop does not have sufficient technical knowledge to fabricate those materials. That means all those things you have to consider, and based upon that you have to select the best material for any particular application. So, with this we come to the conclusion of our today's lecture. In the second lecture we discussed several things. We discussed about the need for understanding the market, and this is important for structural or successful materials design. We also learned that materials design is not only one single parameter game. We have to keep our mind open, and we have to be very choosy, or kind of we have to start from all the materials in the palette, and then kind of narrow our choice to one or two materials. And then we can also see that typically material selection basically require the various steps like design requirements, constraint definition, objective definition, and local conditions. The textbook by Mike Ashby, Material Selection in Mechanical Design, has been referenced for the lecture slides in this lecture, and in the next lecture we will cover the various classes of bulk materials and their properties. That means, we will show that why the hybrid materials are important, what are the limitations of the bulk materials, and we will also give a basic introduction to material property charts and position of hybrid materials, which will be covered in more detail in the future lectures. Thank you very much.